hope that we have an uneventful class, because we could use one. Don't forget that your paper is due very soon, so we should be working on that. And that we have, goodness, please pardon me. We have an exam coming up. That's what I want. So related to that, Ms. Fallon has her exam review session tomorrow at 6 p.m. This is, of course, right before the exam. So you should, very ideally, already be studying. I know this is a very busy week for biology, but the one thing I'm hoping to get out of this is to separate this from your other classes, so you have a little more time to dedicate to studying for this exam, and you're not diverging into trying to split time between, say, chemistry or math. So do make sure that you're trying to work on that. Challenge review session will be very good if there's units that you're stuck on. And of course, by then, we'll have a much better idea of what units we'll have gotten through by then, particularly given how this morning went. I'm certainly going to have to cut some stuff for genetics, which is okay. It is what it is. Every year is a little different. So, okay. Am I screen sharing? Are you recording? Yes. Thank you. All right. So we had just started talking about X-linked or sex-linked. I feel like I'm echoing on that today too. It's like scurry. Allelic relationships at the end of class last time. And these next two that we're going to work through today are some of the most complicated of all of the allelic relationships. The big key here is that we can have two different relationships going on. And the first of which is focusing on sex. All right, and so here's what's going on here. As we look at the X chromosome, the X chromosome is large, or the same size, fundamentally, as all of the other chromosomes that we've talked about up to this point. So in addition to having some standard hormones on it, right, it also has other traits, right, like not death traits, so blood clotting, as well as some hair traits, like balding is on here. Some color traits are on here, like fur and hair color is on here, which is weird, but that's where they are. So the X does a lot of different things. The Y chromosome, on the other hand, is significantly smaller. That's because the Y chromosome performs fundamentally only one task. And that is to create hormones to make boys. So the only thing the Y really does is make maleness. So it's a smaller chromosome, and it mostly only has the genes to do that. So we have sort of all this empty space up here where the genes for balding and the genes for blood clotting and the genes for all of this other business is missing, right, or not there. So this is going to have a substantial effect when we think about how genotypes and phenotypes for males and females express themselves. Right? Because females having, that's on screen, two X's, are going to end up with two alleles. So everything that we've talked about up to this stage is going to function pretty much the same as we would expect it to. Right? So if I'm tracking baldness, Okay, I have a big A for that. And a little a for that, let's say. Okay. Baldness is a recessive phenotype, which is why baldness, by the way, is less frequent in females. All right, so if I were to say this, right, this girl would not be bald, because she has at least one dominant trait to cover up that baldness allele, so she would grow hair normally, fully. Okay. This would be the same if we think about all of the other types of things that we've talked about, right? If I was doing incomplete dominance, we think back to the in-class activity we had with the colored eyes. Okay, I could have two B's, have black eyes. I could have two W's and have white eyes, or I could have a B and a W and have gray eyes. Okay, so this is boring old, same old on ladies. I have two phenotypes though, right? I'm a girl, that's one phenotype. And then I have whatever, right? I'm not bald. That's my second phenotype. Boys, however, cause a bit of a ruckus. Okay? Things on them are going to look fundamentally different. Because we have one X chromosome and one Y. So if we track our baldness one, let's say I have one little a and one, oh, that's right, the Y doesn't do anything, right? So then I have nothing. Okay? So this ends up being a little funky for boys. So whatever the one thing they have, they only get one allele. So whatever that is, that's what they get. Okay, so unfortunately in this case, right, if this little A allele is recessive for baldness, but, right, they have no second allele. Right, so there's no chance to cover that up. So they're going to show this recessive allele. It's the only one they've got, so it gets to speak. You're home alone in your house talking to your cat. Okay? So this is why, for example, men are more prone to baldness. Right? Because when you get that gene, nothing to cover it up. Yep. So what's the male chromosome? Absolutely. So you end up at the mercy of whatever is on the X chromosome. This is exact, and that's the exact example we're going to work through. So it's the same with things like hemophilia, which is blood clotting. Now, this isn't only a male problem. Okay, so, for example, if it was a dominant trait, like Huntington's disease, so I don't want to give males like this feeling like you guys are doomed. Okay? If it's a dominant trait, Huntington's disease, if you're familiar, it's a neurodegenerative disease. It's genetic. It's also on the X chromosome, but it's dominant. Okay? Men are less likely to get that. Okay? And that's just a bad luck of the draw in the ladies, right? Because that means that we just have two chances to pull that allele. And that allele is going to show no matter what, right? Because it's a dominant allele. Okay. But when it comes to these things, right, males tend to show fun. They have no chance of covering it up. And let's think this through for our incomplete dominance. Right, males can have black eyes. Right? They can have a B and get black eyes. Males can have white eyes. They can have a W and have white eyes. But they can't have gray eyes, right? If it were on here. Because you have to have a B and a W to have gray eyes. And they can't have two alleles. They can only have one here. So X-linked changes how some of these things look, and it makes it different for males and females. Okay, so everything ends up looking really dominant in males. And they can't have some of these two-part phenotypes. So let's look at an example of that, and that's what I have up here. We're going to work through this one together. So here I have an example of color, which is also on the X. Color in cats. Okay, so to make a calico, and clearly I didn't set this one up myself because here's the female. So to make a calico, I need two different alleles working together. An X with the O on it, so I'm going to superscript that, make it more clear. Okay, so an orange X and a black X working together give me calico cats. Right, this is a girl cat, right? I have two X's together. All right, so here I have a picture of a calico cat. I have two dominant genes working together, right? Orange and black. Does this look like incomplete dominance or codominance? Codominance, correct. Why did you choose codominance? So this guy's just orange, but you're correct that if it was incomplete, we would expect some kind of third color. And what orange and black makes, I guess it's kind of hard to picture what that would be, right? Some kind of horrific muddy brown color, I don't know, right? But you're absolutely correct, right? If it were incomplete dominance, you expect a blended color. So we would expect some kind of weird, gross blending of black and orange, which I cannot imagine would be terribly pretty, but maybe on a kitty it would be. Okay. In codominance, remember, right, even without any other information on how cats work, remember this is our salad. Okay, so we can go out and we can pick features. So here I can go out, here's some orange, I can pick out orange, right? Here's some black, I can pick out black. So there's my salad. I can pick out the pieces. That tells me, without anything else, that this is codominance on an X chromosome. So it's both X-linked and codominance. Right. Very good. Right, so now let's look at our boy. The X on our boy is black. And then our boy's second gene or chromosome is just a Y, right? Making him a boy, and it has no color on it. Everybody see our parents? And now our key is to make bebés, little kittens. Okay, so the setup for this is the same as it's always been. We're using notation that looks very similar to our regular codominance, right? Okay, XB, XO, XO, and then the Y, so we're making a boy kitty. XB, XB, my B's look questionable. XB, and then the Y. Now remember the key here when we are translating our boxes. So we have two phenotypes. So the first thing I would do when I'm going through is translate the sex. All right, so my first box I have XX, female. Okay. Female. XX, female. XY, male. XY, male. Okay. This also makes a really good checkpoint for you to make sure that you've gotten the appropriate number of X's and Y's in your boxes. Okay, then go back and look at the genes that are sitting on the X's to figure out what the phenotype for the traits that you're tracking are, which in this case, right, is fur color. Okay, so on this first one, we have a B, a black, and an orange. So that's going to make our calico. Okay, on our second one, we have two Bs, so we get black. And on the boys, it's even easier, right? Because we only have one to look at. So whatever that is, what he is. All right, so this X is orange, so we have an orange male. And this X is black, so we have a black male. This is why calico cats are girls, or at least predominantly. Now, does everybody see how we got through building this up? And of course, we're going to practice one together here in a hot second. But does everyone see what we did here when we did this? Right, how we set up our parents and how we got our babies. Now, what's really key here is when we look at our offspring, right? Because there's two different kinds of questions I can ask. We want to make sure that we're very careful on how we read them. So if I were to ask you, what % of offspring are calico? What would you tell me? Well, I just keep writing the word offspring like over and over again. All work and no play make. All right, what % of my offspring are calico? 1 out of 4, right? Or 25%. Okay. What % of females are calico? I heard two different answers there. 1 out of 2. Okay, so this is where we need to be super careful, right? So the first question we're asking, finish that up, 50%, right? The first question we're asking of all of the children, of all of the kittens here, okay, how many of them are calico? Okay, so out of all 4 boxes, 1 of them are calico. Okay, and the second question I've asked, of the girls. Okay, so now I've subset. We have this information, so we can use it. Okay, so of the girls, so I'm only going to pay attention to 2 boxes. There are only 2 girls. So of those girls, how many are calico? Right, and in that case, there's only 1 of them. 50% of females will be calico. Everybody see the difference in those? Okay. This is one of those things you have to be super careful about. They're not meant to be tricky. Okay? This is one of those things like, yay, we have more information, but we have to be really careful because if we have more information, we're going to use that information. Right? We want to make sure we read all of the questions about an X-linked relationship very carefully and clearly. Okay, let's flip over to our in-class activity. We're going to set it up together. Yeah, let's make this bigger. Okay. Okay, so number 5, we will go back to 3, don't worry, is our X-linked. There's a lot of pieces here we need in order to get this going. we're dealing with hemophilia. Okay, this is a clotting or a lack of a blood clotting disorder. And this one's telling us straight out it's X-linked. That's awful nice of it. Okay, but it's leaving a lot of the other stuff super vague. So we know with our legend we're going to have at least 2 X's, and we'll have a Y, but the Y is not going to do much. So we know that the Y is going to make a boy. Okay, so now we need to figure out what is exactly going on these X's. So the information we have is non-carrier or normal female and hemophiliac male. Okay, well, knowing that male is a hemophiliac is not ridiculously helpful, right? Because males often are going to express it no matter what. So let's focus on the female. So it says she's a non-carrier. This means that we have to know what is a carrier. This is a really important term to have. So what does it mean to be a carrier? I have the gene, but I don't express it, right? So I have at least one gene for the disease, but I'm not sick myself. Okay, so if I can't actually get or express a trait, okay, but I'm carrying it around hidden, okay, what kind of allele, dominant or recessive, does that indicate that that is? It's hidden. Recessive, good. Okay, so a carrier is going to be a heterozygous. Wow, that could not be written worse. Okay, and the important key information here is that recessive is the trait or the thing we're following. Okay, in this case, we're talking about a disease, but it doesn't have to be, right? Again, we can be talking about baldness or color or any sorts of thing, right? But it's something that you carry but don't express. And you're not expressing it right because the dominant is covers. Okay, so in this case, right, if we know the recessive is the trait, we know that our disease is recessive. That's what this is telling us, right? Because we can have carriers. Everybody follow that logic? And now, we do know that mom is not a carrier, but this tells us a lot. So we'll have, I'm just going to use H's, you don't have to. Okay. The recessive is the trait, so my little one here is going to be hemophilia. Okay, and my capital letter then will be a non. I'm going to abbreviate because I am quickly running out of room. All right, so let's look at what mom and dad would have to be then. Okay, if mom is a non-carrier, we know she's a girl, so she has 2 X's. What is on her X's? One more time for me, I'm so sorry. 2 dominants, good, perfect. So she's not sick, and she's not a carrier. So that leaves us only one choice. Now let's look at dad. He has to have an X and a Y. That Y is not going to have anything. One less thing to worry about. What's on his X? recessive, right? Because this is telling us the dad is sick. Sick is loose. You can do very well with hemophilia these days. It's not like it's the 1600s anymore. Not the Romanovs. He'll be fine. Okay. I'm going to let you work on working through this, but remember one thing. Okay, just like with incomplete dominance, okay, the X with the superscripts are all one allele, okay, just like the I with the superscript was all one allele as you go to move forward. So go ahead and make some gametes and set this up, and then we'll work through part of this together, just like we have been doing. Okay, let's make some gametes. All right. Mom has 2 alleles for 1 gene. So she's going to make 2 eggs. Okay, remember that superscript is just expressing which trait we're following. So the X and the H are going to stay together. Okay. We do the same thing for Dad. He has 2 alleles. You know, it seems weird because the X and the Y seem different, but they're just variants of the same thing. We're going to put the Y in that one because it's a little. A very nice looking sperm, if I do say so myself today. Now, when we set up our Punnett squares, right, this is ultimately the same old, same old. Okay, put mom on top, pop on the side. And remember, it's one gamete per box. When I put mom across the top, it's one egg over each. When I put dad along the side, it's one sperm over each. Now again, remember, the only thing we really want to pay attention to here is we want to put things in order, dominant first, right? That makes translating these so much easier. So as I make my babies, my dominant letter is going to come first, then my recessive. And I'm going to do the same thing with the Y's, right? That's why the Y is always written second. The Y never even has anything on it, so it's always, right, the recessive one. Because it never gets translated for whatever trait we're interested in. Okay. How many children have hemophilia? 0. Right? Remember, hemophilia is a recessive disorder. So in order to get the recessive disorder, you either need two little h's, or you need to be like dad. Be X, little h, and Y. Right? So you need that recessive allele to do the talking. And none of our children here have that. Okay. The boys are in a really good position in this family, right? Because they have to get the Y from dad. Right? Dad gives all of his boys his Y. That's what makes them boys, right? So their X has to come from mom. And the mom in this family has no little h's to give. Right? She has no hemophilia alleles to give. So none of the boys in this family can be hemophiliacs, which is what we see here. And now the girls in this family are all what? Carriers. All of the girls are carriers, right? Because the dad, right, has to give all the girls in the family his X, right? Males define sex. Right? They're going to give them an X, or they're going to give them a Y. Where it comes from, right? So dad's going to give his X. His X only has, right, that little H on it. So all of the girls in the family are going to get at least one little H. And thankfully for them, mom only has big H. So all of the girls are carriers here. Okay, so remember, being a carrier means they don't have it. Right, so these girls are not hemophiliacs, but they carry the allele for it. So if they have children, if they could have children that are hemophiliacs, if they pass on their little h. Okay. As usual, make sure you work through these. I want to make sure we work through this bottom question on what type of inheritance this is. Okay, so for the first time ever, we're going to, I think first time ever, I might be talking too soon. We are circling more than one of these. So which ones should we be circling? X-linked for sure. There we go. And we know that because we were dealing with males and females. You can pretty much be assured if a question says something about males and females, bother to give you the information, you've got to use it. Okay. What other type are we dealing with here? In other words, what's the relationship between the other two alleles? We have two alleles, a big H and a little h. What is their relationship with each other? Simple dominance. Right, so this should look a lot like your first in-class activity, right? You have one dominant and one recessive. Okay, the one from our lecture, the kitties, that was X-linked and codominant. Any questions about what we've done here? All right, so the last complication to talk about. Polygenic, Gesundheit. Literally meaning more than one gene. Okay, so everything we've done right up to this point may have more than two alleles. Okay, if we think about like incomplete dominance, right? It had more than two alleles involved, right? But it was never more than one gene. Okay. The one problem we ran into is ultimately that did limit us a little bit on how much variation we could get. The most we got out of codominance, the most we got out of codominance was 4. Right, we got 4 different phenotypes, which is good. But certainly if we think about all the variation that we see, not even close. So how is it if we think about something like eye color, skin color? Okay? How do we get the wide variety of gradients that we actually see? And the answer is, well, a lot of these things are more than one gene. Okay. So if we look at the example that I have here, I've got this set up with 2. Okay. The A gene and the B gene. And these 2 genes work together to create a rainbow of color that make eyes. So if we start in the upper left-hand corner, okay, what I mean by this is if these 2 genes, if all 4 alleles are dominant, you see we get the darkest color eyes. Okay, so the relationship between all 4 of these alleles is going to signify a very particular outcome. Okay, on the far opposite end, the bottom right-hand corner, if all 4 of these alleles are recessive, I get the lightest color. Blue. A little reductive, so you can already guess it's probably even more complicated than this, but this is good enough for as far as we need to go. Okay, so then if you look at the middle spread, okay, we darken or lighten eye color by a combination of how many dominant alleles you get out of those 4. If I look at my greens, what I've done is I have one dominant allele. So by having 1 out of 4 dominant alleles, I get to slightly darken my eyes from blue to green. Okay, to get this, like, I don't know, taupey hazel color. I have 2 dominant alleles. Okay? So this relationship, or this higher frequency of combinations that I can get by having more genes, changes the number of colors I can get. And we have more colors of eyes than this, you can imagine there are more genes, more combinations that allow us to get the variations that we have. Same thing with skin tone. Conceptually with me? Does this make sense? Right, so having more genes, having more alleles to play with gives us more variety. Now, there's many different ways that multiple genes can work together to create a very specific outcome. Without maybe realizing it, you actually dealt with one of these already. And that's the specific example we're going to work through together. And that's epistasis. So instead of working together to create a gradient, these sort of work as an on-off switch together. So here we have 2 genes, okay, that create a larger gradient. But it's not the combination of alleles that necessarily does that here. Here we have 2 genes. My first gene in this particular case is what's creating some kind of color. Okay. So here it's my B's. Okay, so you can see if I have a capital B, if I'm homozygous dominant, right, or if I'm heterozygous, I'm going to get a black lab. Or if I'm homozygous recessive, I'm going to get a chocolate lab. Okay. So that's pretty boring, right? Most of the time we see these as like simple dominance. This is the first kind of example we ever did. It's not that exciting. What makes this interesting is the second trait. Which works a bit like an on-off switch. And this is what we see here, which is the E's. Okay, so we see here, in both the black and the chocolate labs, as long as I have at least one capital E, whether I'm homozygous dominant or heterozygous, I'll make color. But if I'm recessive, then I don't make color at all. I end up with a yellow lab. So here's, I call this the oven gene. Okay, so our first gene, the gene that makes the trait, is like the oven dial, the one that makes the temperature, right? I can set this to whatever temperature I want, 250, 400 degrees. Okay? I can make all sorts of different temperatures. But my second gene here is the oven plug. Okay, so if I have a capital letter, then my oven's plugged in. It'll actually turn on, it'll heat up, make color, right? But if I have all recessive, then I've unplugged my oven. Okay, and if I unplug my oven, then I can turn my oven on to 800 degrees and set it to broil. Nothing is going to happen, right? My oven is never going to get hot. And that's what happens here, right? And so that's what we mean by all these question marks. Doesn't matter what's sitting there. I'm never going to make chocolate or black labs, right? It's always going to stay a white dog. Because I've unplugged the oven. I've turned that gene off. Okay, so you guys did this too. You made white dragons. Definition work okay? All right. Let's work through an example of this. So we're finally going to go back to question 3. And there's a reason we skipped it. And the reason is where it is because it needed its own page. Okay. So the legend here is mostly given for you. And so I'm going to give you most of this time to work. And then we'll touch on this again in class next time. What I really want to talk about is how to make gametes. I'm just going to make a dog up. Random dog. Very unlikely that's one of the dogs there. Possibly. I have no idea. I did not read it. The key here, though, is if we look back at our example, and this happens to be the same sort of setup, right, is we are polygenic. I have more than one gene. Remember, when I'm making gametes, that I want to be haploid, but I need to be haploid for every gene, right? So my gametes need to have a B and an E in them. Otherwise, you're going to get weird mutant puppies, and they're going to be sad puppies, and nobody's going to adopt them. Okay, so in order to make sure I end up with good gametes, I go about doing this using an old math foiling method. And so here's what I mean by this. I'm going to start with my first B. Let's not use that color. And I'm going to combine it with the first E. That's my first gamete. It has one B and one E in it. And then I'm going to do the same thing. I'm going to grab that first B again. I'm going to combine it with that second E. That's my second gamete. It has one B and one E. And now we're going to do it again with my second B. I'm going to take that second B and I'm going to combine it with my first E. That's my third gamete. One B and one E. Okay. We're going to do it one last time. I'm going to take that B, combine it with that last E. My final gamete, one B, one E. Okay. So this is how we want to check ourselves. All of our gametes are still haploid, right? We only have one of each gamete. And now for the first time, right, we have 4 gametes instead of 2. And this is why this one has a whole page of space to work with instead of just a little half like we've been working with. So work on setting that up. This will be pretty much the last thing we do, besides one other definition. So we'll go through a solution together. Isaac. This would be just one dog. So if this was my girl, this would be just eggs. And you would do this again with a boy. You would do the same thing, correct?
Do they in e-learn just change that, or?
Yeah, that's just not updated from, I don't know, last year or something. So